As promised, this is your review slides for exam number 2, GIS 201. We're going to cover some of the material. I'll go over parts of it rather quickly. Some parts I'll speak on a little longer, but in general, you know that the questions come from these slides. And at the end, there is a special set of 12 repeat slides that the 6 essay questions or matching or the non-matching part of the test at the end will come from these final 12 slides. So we'll work through it, and hopefully this will help all of you achieve your desired outcomes on this next exam. So you need to be able to explain what a spatial join is. You need to understand what's behind that. Know that when you do a spatial join, you have a destination and a source, and that they have to have a common field. Destination and source, I'm not going to really, push that a lot, so you don't really need to be able to explain that, because as long as you can figure it out as to which one the data is going to, that's all you really need to know. So remember, joins two tables based on common spatial relationship. Things like one feature inside of another, or one feature closest to another. That is the basic way a spatial join works. Distance spatial join appends records based on which source feature is closest to the destination. An inside join appends the records of the source feature to the destination feature. In this example, you have wells that fall inside of a certain geology, so the well would then have its geology associated with it. Cardinality has to do with the relationship between the features in a join. If you switch your destination back and forth between some of these examples, what would work one way will no longer work, because instead of joining one-to-one, you're joining many-to-one, which is a no-no. That's when you have to do a summarized join. And in those examples, you can look through these and understand what they are, but essentially it just takes and finds which cities are closest to which airports. And that's sort of how this example works. It identifies all of those, so the cities would be the many and the airport would be the one. Summarized joins are specifically designed to handle these sorts of relationships. The cardinality, spatial join cardinality is pretty straightforward. Simple joins are one-to-one or many-to-one, and summarized joins are one-to-many or many-to-many. This is an example of simple joins of a summarized join. How you can join points to points. They can be distance joins only. Simple or summarized depends on the question that you're asking. Which attraction closest to which hotel? How many attractions are closer to one hotel than another? So it could be many-to-one or one-to-one, but they are distance joins only. Types of spatial joins. Here is a really good diagram. Simple versus summarized, inside versus distance. Feature geometry and spatial joins. You can have points to polygons on a distance. Note on polygon distances, they measure from the centroid. Centroid doesn't always occur in the center, so you have to be careful about that. You can also have points to lines. This is an example. The text there explains something well. Feature types. Every join involves two geometry types. You're talking points to points, polygons to lines, lines to points, etc. Each combination offers two possible join types. Usually one is a simple one and one is a summarized one. So this is the part where the textbook does things backwards for no good reason. And I left that in just because it really irritates me that they do that. And anytime I get the opportunity to share that with you guys, I enjoy telling you that. So this shows you the different types of joins and an example of each. If you can understand this, you're in pretty good shape as far as understanding the different types of joins. More examples of points, examples of polygons to points, examples of polygons. Be very cautious and make sure that what you're doing makes sense. and has meaning, because sometimes some of the possible things you can run really don't tell you anything. Polygons to polygons. Simple insight is like give an urban area all the attributes of the county that it falls in. Summarized would be to give the county summarized attributes of all of its urban areas. Some more examples. Options. There are only a few options that are possible as far as the combinations. It seems really complicated, but ArcGIS really helps you out, because once you start the process of doing the join and you select which is your destination and which is the other one, it narrows it down and it gives you one or two options, and it kind of keeps that the number of options you have to pick at any one time at a minimum, and that makes it easy to work your way through and do the right thing. Coordinate systems and distance joins. You need to make sure that your coordinate system is in a projected coordinate system before you do any kind of a join based on distance, because obviously the distance would be in angular degrees, which would not be very helpful for this kind of stuff. So you want to be in a projected coordinate system. The other thing is you should be in a projected coordinate system that preserves the property that you're interested in, i.e. distance. There you can see the units. Distance are given in stored units. Decimal degrees cannot be easily converted to miles or kilometers. So here we've got a couple of different coordinate systems. One is in geographic and one is in UTM, and you can see that the same process gives you a different result if you're in a different coordinate system. So you just stay away from the geographic coordinate systems for any type of analysis. Again, beware, data frame coordinate systems may be different than the source data coordinate systems, and setting the data frame coordinate systems is not enough to fix the problem. Data itself has to be in a projected coordinate system, so you need to use the project tool. Joins are pretty simple and straightforward. Here's the box, there's the options. There's your two choices. There's the different things that you can choose as far as the summary statistics. And this is the kind of thing that I'll ask questions about, like over the last couple slides. I like things like, unlike the summarize command that pairs stats with specific fields, if joins, you only pick the type of statistics. And so I might talk about that and then ask you a question about how they're different or something. Map overlay. It's kind of like a souped up join. Joins features based on common location, forces features to split, effectively generating and enforcing a one-to-one cardinality between features that allows everything to be the attributes to be joined. So why do we do it? Because spatial joins don't always work for what we want. Sometimes we need features that don't fall neatly inside others, and the overlay provides us a way to split these features up so that there's always a one-to-one correspondence, so that we always have all the data and we don't have to summarize. Other problems with spatial joins: together statistics on the total length of a road. You want the associate land type with each part, and you need to do something because the roads don't stop at the boundaries, and so summarized joins don't work, and they don't work with categorical data as well. So there's just lots of things that they fail at, and that's where things like overlay functions can come in. Map overlay splits these things so that you can now have all that stuff. Types of overlay: point in polygon, line in polygon, polygon on polygon. Point in polygon is used to assign polygon attributes to the points. Points and polygons attaches land use polygon attributes to each school. Line in polygon overlay is used to assign polygon attributes to the various lines in each of the segments. So you can attach, for example, the geology to each part of the road or the stream. Lines and polygons: each stream acquires a geologic unit from the polygon that it lies inside of. Just kind of what I said in the previous slide. Example of combining the two layers to get all the possible combinations to have an enforced one-to-one cardinality that then allows the attribute tables to be combined, so that for every possible fragment on that map, you now have information on the geology and the slope class. Understand the steps to the overlay process. Combine features spatially, producing all new ones, combine attributes, etc. Just another slide to illustrate how it works. I'm sorry here. Let's take a look at this. The types of overlays. Union combines all, intersect combines and only keeps common features. So this is what overlays happen. The top is intersect, where you only find the features common to both data layers, and that would be the purple. The bottom, you use the union function. It keeps all the areas from both of the layers on the left, and you end up with the purple areas on the bottom. Just another example of a union. Intersect examples. Residential areas and certain geologic formations. You can use the intersect to find areas that are in both. Hazard mapping, habitat analysis with intersect. There's lots of ways you can use it, and you can get different geometries. You can use the intersect tool to get the polygons. You can get it to do lines, or you can get it to do points. The output dimension must be less than or the same as the lowest input dimension. So if you're intersecting lines, your only options are lines or points. If you're intersecting polygons, you can have polygons, lines, or points. If you're intersecting, well, that's it. This just shows how you could use intersecting lines and polygons, but maybe what you really want is points, so that you have the coordinates to go set up the roadblocks to catch the bad guys leaving from the bank robbery that was in the center of the circle. Here are the different types of overlay operations that we commonly use: clip, erase, intersect, and union. You have your inputs, you have your overlays, and you see the assorted output that you get from those. Clip and erase attributes are not joined. Intersect and union attributes are. Length and area changes. Clip and erase change some of the features, and so some of the areas and some of the boundaries are going to be changed once you use these processes. Geodatabase feature classes have a shape underscore length and a shape underscore area field that are automatically updated. In every other instance, these numbers are not updated. Always assume that area and length calculations are incorrect until you know otherwise. Dissolving is a technique that works off of a single field to dissolve polygons or lines into single features. It eliminates all the attributes in the table except for the one you dissolved on. That's the downside. Now you could choose to summarize the other ones. Buffering is pretty straightforward. It just creates a boundary around a feature out to the distance you specify where the distance is. Append is another tool. It places features from one feature class into an existing feature class of the same type. Unlike union, it does not attempt to split or change features. It simply brings things in, and so if it's something that's already there, you end up with double features. Merge combines two feature classes of the same type into a new combined feature class. Merge does not attempt to split or change, and it does allow for overlapping as well. Efficient overlay is when we look at our overlay process, because it can be time and memory intensive, and we minimize the number of features by dissolving things before we intersect them with other layers. Slivers are those tiny little pesky things that occur because boundaries create these little polygon bits because things weren't quite coincidental or any number of reasons. But what you need to remember is they're tiny polygons created during geoprocessing. They're the result of slight differences in boundaries. They can build up because of multiple operations, and they are a nuisance. You can adjust your tolerances to help deal with it, but that's tricky because if you set your tolerances too far in one direction, it doesn't take them out. And if you take it too far in the other way, it can impact your accuracy. Geoprocessing is basically the executing analysis functions and tools, stringing together analysis functions to achieve a result. XY tolerances, feature class property set at the time it's created. It's the minimum allowed distance between two vertices. It's used to cluster nearby vertices during geometry operations such as clip and intersect. The default is intended to preserve accuracy, and you can see what those defaults are. And then we have an example up here of what an overlap is and what a gap is. Overlap being areas where the two polygons cover the same space, and a gap being an area where they don't cover in between them. You can use tolerances to reduce slivers and other things. This is what happens. I showed you the effects of changing your tolerances. You can see what the default is and what happens when you set it to 500, 1,000, or 1,500 meters, and how it changes the shape of the polygon. Coordinating systems and geoprocessing. There's some issues you always need to be aware of. Geoprocessing often involves areas of length, so you need to use a projected coordinate system. If not otherwise defined, the output coordinate system defaults to the first one brought in, so you need to get your stuff right before you start setting this up. Reprojections will be done during processing if needed, but it's better to control it if they're done, so it's better for you to do that up front. A good analyst is always aware of the coordinate system being used during processing. Best practices for analysis: choose a coordinate system that leaves, instead of leaving data in a GCS or taking it by chance, select a projection with a minimal distortion for the study region you're using. Convert all data sets to the same coordinate system. Ensure the data frame is also in the same coordinate system as the data that you're working with. Background processing, turn it off. The intersect tool looks like this. These were the dissolving tools, like the buffer tool, areas of features, areas and lengths are important, geodatabase shape underscore area and shape underscore length are automatically updated, but that is it, nothing else. No shape files update anything. How do you update stuff? You select the right column, you use the calculate geometry, select the property that you want, the projection system that you're in, the units that you need, then you click OK. Model Builder. Model Builder. Create models built from sequences of tools, more processing steps for later reference. It allows you to execute models repeatedly with different inputs and share models with others. That's what Model Builder does. That's 4 good reasons to use it. So if I said, why would you use it? Create models from sequences of tools, store processing steps for later reference, to execute models repeatedly with different inputs, and to share models with other people. This just shows the steps of how you go about building them. Same way for a new toolbox. Why would you want to use rasters? This is kind of one of those questions that would make a good test question, and you would answer it with, like, better at storing certain things, better at analyzing certain stuff, usually faster than vector. Imagery comes in that format. If I ask you why would you not want to use it, you can say the coordinate precision is generally lower, high precision increases the storage costs, and you cannot store multiple attributes. Raster resolution is measured by the cell size dimensions. Storage space increases as the square of the resolution. As your raster resolution gets smaller, your storage space gets significantly bigger. Raster analysis. Basic concept is the grids line up so that you can multiply a particular cell in one grid by its corresponding partners in the others. It only works if everything is the same size and lined up spatially. That means you need to make sure that all the data is projected the same way. Resampling is when you create some new grid spacing and it doesn't line up with the old one, so you have to figure out a way to populate the new one, and you use some sort of a resampling algorithm or technique to do that. Here is the resampling methods that we use. Nearest neighbor, bilinear, cubic convolution. Nearest neighbor picks the nearest one to the center of the new cell. Bilinear looks at the 4 closest cell centers and calculates a distance uses a distance-weighted algorithm to calculate a new value. Cubic convolution looks at the cell centers of the 16 closest cells and then does the same, calculates a distance-weighted algorithm back to your store ID or location, and then from that you can figure out what it is. Nearest neighbor gives you the sharpest image. Cubic convolution blurs or dulls or your data more than the others. Bilinear is somewhere in between. Cubic is the slowest. Nearest neighbor is the fastest. Caution. GIS will automatically resample stuff if it needs to, and it doesn't warn you, and it doesn't tell you, and it doesn't give you a whole lot of options. It's best to try to keep all of your analysis in data, aligned rasters, common extents, common cell sizes, using your environment settings to enforce common grids, that kind of stuff. So what are some analysis techniques? Let's look at map algebra and Boolean and some other stuff. Map algebra is pretty simple. You have layers. You introduce math functions, and then the corresponding cells from one layer to the next are simply elements within the math, and the math generates an output. This just shows you how you can potentially use something like that to convert rain in centimeters to rain in inches. You can also use this sort of stuff to calculate cut fill by subtracting a final surface from an initial. You can model all kinds of complex things if you have an equation that predicts a particular situation. Here are some other examples of some true, false, and 1, 0 Boolean kind of outputs. Elevation over a certain area, the part that is becomes one color, everything else stays the same. You can classify your slope into one or two categories, less than 10 or above 10, and so you can identify areas easily that way. Same way you can do the same thing with land cover. You can identify the categories that meet your conditions and assign values of 1, and for the areas that don't, they get scored 0. You can use these Boolean raster representations of true and false for a lot of different things. You can also use some of the other functions like and or and not and whatnot. These are some examples of how that works using the little circular representations and then the grid on the right. And you can see that the areas that are yellow is true and the areas that are not are false, and how that comes out relative to using an and or an or function, an intersect or a union. More examples. Shows how a real-life model could run through that and what that would generate. Looking at precipitation and elevation requirements for something, just like that, Bob's your uncle, and you've got this new habitat map. You can also use multiplication instead of just addition. The additive model takes layers, takes the values, and adds it together so that you end up with areas that meet one of the criteria, both of the criteria, or none of the criteria. Drawbacks of this type of overlay is they're basically just real simple kind of true-false things. Doesn't support a lot of gradation of suitability. It assumes everything's equal. Okay, had to record this slide over, guys. My mind started wandering there in the middle of it, and I started out talking about weighted overlay, and in the end I was talking about go-karts. So let's try that again. Not always is everything equal. Sometimes you can use a weighted overlay function where you reclassify your raster inputs into rank suitability, weighing each input according to its individual importance, which you then use to calculate your suitability index, where you have this particular model here as an example with the weight for each input multiplied by the rank of each input. And it has nothing to do with go-karts. Suitability. This is an example of that. We have this overall suitability that's made up of slope and infiltration, distance to roads and distance to streams, and then we have a weight assigned to each of these relative to our importance, and then each one is classified into 3 categories with a score of 1, 2, or 3, and then from that you end up with this mathematical model that generates this map on the right that shows the areas that are most suitable and least suitable for landfill. So you can also combine this stuff with Boolean stuff like true-false stuff. It's really good to set off area limits using zeros to multiply in to eliminate locations that you just don't want to do with. And that's what we did in this example here. And you can see the grayed out areas as parts of this location that was Forest Service land, and we couldn't build there anyway, so we had to identify potential habitat or potential building sites for a cabin on other properties. This is a raster calculator. It does all kinds of math and stuff. Other functions, analysis techniques that are common in raster would be these lists. Anytime you see a bulleted list like on this slides that I leave behind, it's probably a good idea if you know at least a few of those enough that if I ask you to name 4 or 5 of these, you could. Reclassification, you take the old values, you input new values, you can utilize no data and many other things to change what is actually identified in the raster. Surface analysis, again, this is a good 5 things that you should be able to at least list and explain a little bit as far as rasters and surface analysis. DEM, slope, aspect, hill shading, and contouring are all types of surface analysis. Slope function, how it's calculated, rise over run, percents or degrees. Aspect is the direction of the steepest slope. Hill shade is essentially allowing the software to position the sun relative to your inputs and see what areas would be in full sunlight and what would be shaded, and then from that shaded you can get a better understanding of the look of the landscape. Viewshed, it's simply the area that can be seen from a set observation point. Cut and fill, the initial surfaces, and you can figure out in some areas how much you have to add, in other areas how much you remove. You can also do hydrologic functions like drive streams and watersheds and that sort of stuff. Distance functions can be simple like a cost path or a buffer or a continuous distance layer. Euclidean distance starts from a set of points and lines that creates a grid looking for the distance to the closest feature. Euclidean direction is similar, but it indicates the direction of travel to the closest feature. Talked about buffer. Interpolation is the prediction of values in between measured points. Sampling of points may be uniform, random, or based on some sampling scheme. There are lots of methods out there. The best application of interpolation relies on substantial study of models and assumptions. If you use this sort of stuff a lot, you really need to spend more time learning about the various interpolation techniques so you select the right one. Here are some examples of values that we know based on stations that measure precipitation, and from those known values we generate this surface that indicates what precipitation is like across the entire study area. Interpolation is not the truth. It is simply this calculated surface between known points. It's the best guess for the unknown. In this example, we have elevation of the various peaks in a watershed or this area. If we calculate the surface elevation from just those peaks, it is not like the actual model, and that's the point. Interpolated surfaces are only as good as the input, and if the input is only the high spots, it's not going to adequately reflect what the low spots and everything else looks like. So interpolation is indeed not a truth. It is an estimation. As soon as nearby points are correlated, in other words, they have similar values, there's 4 types of interpolation methods that are available in Spatial Analyst. You should know that that's inverse distance weighted splines, kriging, and trend. Know what a density function is, and it has nothing to do with the attributes. It has specifically to do with the number of observations in a given area, not what was actually observed. 2 types, simple and kernel. That's really all you need to know about that. Neighborhoods calculate a statistic for a specific window, and there's different shapes they could be as well. Windows move. They can move in blocks, in other words, one giant chunk of grid at a time, or they can move cell by cell and then reestablish that new window around that cell and calculate the values for that one and then move on. One's called a block function, one's called a focal function. One allows overlap, the other does not. Focal versus block, you can see how that changes the output. Again, that's what it looks like. This is what it does to this DEM. You can also use it neighborhood focal majority filter. After a couple of passes, you can go from something like that to something much more easy to identify. What is a zonal function? It examines and manipulates the raster values in one within one set of specified by another. Essentially, the way it works is you got this data and you want to calculate it up zonally. It uses another data set to identify the zones, and then it calculates the values from the first data set relative to the spatial parameters and outlines of the other. What is a zone? It's not AutoZone. It's an area with a raster feature data set that share the same energy value. Zonal statistics. You simply calculate the statistics up for the individual zones. You can do it for lines or polygons. You can also do it for points. Raster formats, inputs. Spatial Analyst supports any raster format in ArcGIS. It outputs things as grids, geodatabase rasters, TIFFs, or ERDAs. It stores integer or floating point values. Other formats that you deal with occasionally would be JPEGs, GIFs, Mr. SIDs, raw, binary, etc. These tend to be for display only. Most formats are proprietary and include some sort of compression scheme to reduce the storage size. So find something that works, and that's usually the way you go. As your grid format, notice not has to be less than 13 characters. That's the big thing I want you to catch. Managing rasters means working directories tend to get clogged with a lot of grids. You copy, move, and delete stuff only in our catalog. The best practice is to create a geodatabase to store your analysis outputs. Zone is a collection of all the cells sharing the same integer value. Zones need not be contiguous cells. Most useful with discrete integer rasters. Grid attributes, you only really get a couple of things: the value in the cell and the number of the cell. No data is really useful. When you reclassify, you can select certain variables and say that's really not data. It's no data, and it leaves it as a blank spot, indicating that it's nothing there. Sometimes you might want to use a 0 in that format. It just depends on what you're trying to do with that layer. So you might want to put the 0 layer in if it allows you to see something, or take it out if you want to get rid of something. Converting vector to raster is rasterization. Converting features to raster is rasterization. Converting features to raster is rasterization. Convert selected features. If a selected feature has a selection, only the selected features are converted. I want to point out that when you're doing this, some things are really complex and they're really difficult to do. So you want to use the simplify polygons option if you want to efficiently make some of these changes. You can get something that's okay. Neighborhood majority is useful for simplifying rasters prior to conversion. 5x5 majority filter really is can be pretty helpful after a couple of passes. Rasters to polygons, that is vectorization. Again, vectorization. And you basically get this grid code value at each polygon, and that corresponds to the actual value in the attribute table of the raster grid. What do you do with no data? Well, nothing. If there's no data, there's no data. But if it's a 1 or a 0, it ends up as a polygon with a 1 or a 0. So you can use no data values when you reclassify things. In this example, if 1 is the area that you're looking for, you can reclassify the no data and zeros to all no datas, and then you're left with simply a 1. And then when you convert it to polygons, you get to the thing on the bottom right. Reclassifying, lots of ways to do that. Using Spatial Analyst, it's an extension in our toolbox, all kinds of cool stuff. Analysis mask is one of those. Analysis mask is essentially the cookie cutter layer that you can use to direct the analysis that you're doing, and you can actually use the mask as a tool to clip rasters. Clipping a raster, using the function extract by mask, you input the mask, which could be a polygon or another raster, and then from that it will trim up your raster into that confined space. Topology rules are things like adjacent polygons must share a coincident boundary that is exactly the same for both. There are no gaps or overlaps between adjacent polygons. That would be a topology rule for polygons. This would be a topology rule example for lines. This would be one for intersections. This would be one for nodes. Again, as we go through these, I'm not going to read them out and talk too much about them, just skip. But there are different types of topology rules. You should be able to list and name a couple of rules for each of the different geometries that we deal with, points, lines, polygons, etc. More of the same stuff. So what are some of the problems when you hear topology is all whack? Well, sometimes it's undetectable and the errors don't show up in the maps and it doesn't interfere with analysis, and so it's really not a problem. Sometime when you zoom in, you can see little things that makes your maps look a little bit off, and that's a minor annoyance. Sometimes it kills your analysis dead in the tracks, and sometimes there's legal issues and liabilities from it. So the bottom line is the severity depends. So there are some exceptions. Sometimes you set up all these rules and things are supposed to go, and then all of a sudden you find a cul-de-sac, which is a dead-end road. It's not a dangle, and you don't want to remove or fix it. You leave it where it is. And that's where exceptions come in, because you can say this is the way it's supposed to be. I'm going to call it an exception. It doesn't need to be fixed. Quit identifying it whenever we check to see if our topology works. What we're shooting for is logical consistency. In other words, we want our virtual environment within inside the GIS to represent the real world conditions. If a road meets another road and forms an intersection, then we need a node and we need an intersection. If one road overlaps another road, because one road in fact is an overpass over the other road, and there should not be a node there, and there is no need to join anything at that point. It should have some sort of overlap. Spaghetti models, and know the difference between a logical or between a spaghetti model and a topological model. Spaghetti models don't store topology. Each individual item or feature has another topology with it. It is simply exists, and that means that some things overlap and some things share boundaries and some things share parts of boundaries, and it can be a mess. Whereas in a topological model, there's order and structure defined and created by the implementation of the various rules. There we go. Digitizing, what makes it challenging? Well, it's a lot of work. And so there's a couple ways you can do it. You can divide and conquer, and you do some things, I do others. We can start by creating a square outside boundary. We can use the cut polygon tool to carve things out. We can add polygons, but what you don't want to do is go in and start drawing, for example, polygon 6, and then go in and draw polygon 7. You want to take polygon 7 and add it on to the boundaries of polygon 6, not the other way around. You want to eliminate trying to draw lines that are coincident. They should be a single line, and then you build off of it, not trying to trace back over top of it. More examples and such. Combining and buffering features. This is what merge can do. This is what union can do. This is what intersection can do. This is what buffering looks like. Stream digitizing. It's basically digitizing, but you just roll the mouse around the area very deliberately, and it automatically throws out points, signals your phone to identify where you're at or where it's at, and from that media, it eventually completes the circle back around to the beginning. Sometimes that's bad because it ends up putting a lot of nodes in. Most people prefer the point-and-click method. That's the point-to-point advantage. That's where you just go around and you click the things wherever it stops and you do that. It's more efficient, doesn't store as much data, it tends to work a lot easier. Problem is, you really need something more robust than that, because these data volumes can get pretty efficiently large. So what are some of the advantages? There they are. You can read stream tolerance, understand what it means, and how if you get it too much or not enough, it can lead to having too much data or having too much data, both of which are not situations that we're kind of looking for. Modifying feature, it's your editing tools, buddy. It's the ones you use. You go in there, you select something. Once you select it, you use whatever tools you want. When you click on the tool, it lights up, dances, sparkles, whatever it's supposed to do, and then you can do what you need to do. There's also ways to reshape features. You can also flip it around. You can have multi-parts like the Hawaiian Islands, where each island is individually drawn and completed, but yet it still gives you the ability to go back later and attach things to individual bones or individual components of that thing. Think of the islands like your fingers, and a multipart can be disjointed. In other words, the fingers can be independent, and that can be helpful because you can put attributes for each one. Construct points. You can place them along a line by distance or by number, or just put them wherever you want. Moving exact distance, you can tell it that you need to move your feature so many degrees in X and so many degrees in Y, and it will do it. You can also copy the things in parallel. Preventing topological error is difficult. It comes down to editing, and you want to be very good at it and very cautious and very deliberate. Take your time. You want to use snapping. You want to split lines. You want to auto-complete polygons. You want to cut polygons. And you want to clip. And then you want to use your map topology and shared editing to fix anything that doesn't take care of. Snapping is another set of tools that you use sometimes. There's different types of snapping, depends on what you snap to. And that can make things like undershots actually form nodes and overshots come back and form a node. Avoiding improper intersections, you can split lines, you can snap to a vertex. Use polygon complete tool to draw certain things. Use polygon cut tools to divide things up. Use the clip to eliminate overlap areas. There's tons of ways you can do this stuff, and this is just some of the ones they recommend. Clipping, you can tell it to preserve the things that you clip out or to discard. It's important to know that. Essentially, we're talking about a giant geographic cookie cutter, and we use it to separate things. Some more examples. Map topology. Map topology allows features to be shared, binary or nodes to be edited simultaneously. Essentially, map topology controls the interactions between all the features. Cluster tolerances, how close does something have to be to actually be something that's combined together. You can set those and adjust them. You just got to be cautious. At some point in time, you'll be ready to create your map topology. Just follow through with the instructions. When the topology toolbar is done, you can control various things in it and edit various other things as well. You get something that looks like some of these, and then you might have to go back in and edit, move some things around to make it all work. But you can move shared features with some of the tools, and so that's helpful. But you can't do it all the time. Stretch geometry option is another one. Allows you to sort of drag and pull your lines around. Modifying a shared edge between two features is another popular. You can reshape a shared edge. Planar topology. It's one of the early on parts of what we do, or what we'd like to think we do. It depends really on what you're working on, but if you're working on certain data sets, understanding and implementing topology is really fundamental to being successful. So what is it? Rules that define the types of spatial relationships that features may have with other features. Features that violate these rules are considered to be errors, and it ensures behavior and consistency of features. Planar topology allows the setting of rules governing topology within and between layers. It has tools for finding and fixing errors. That's the big one. So you set the topology up, and then it looks for things that violate it, and you can fix those, and then look again, and ultimately you'll get to a point where you've fixed it all. Some examples of what happens when topology is all out of whack. Some examples of some rules. A line from one layer must not overlap lines from the same layer. A line from one layer must touch lines from the same or both layers. Implementing topology can be fairly straightforward. Rules are defined within the feature data set. There are special tools to do this with. Validation is used to mark errors and for editing, and then you can go back and fix them until you end up with a data set that doesn't have any errors, i.e. Everything's good. Well, the types of rules, there are different ones for each one. You need to know a few different ones for some of the questions. Here are some examples of rules for lines, examples of rules for lines, examples of point rules, examples of two-class rules. When you validate it, software checks for everything, looks at your snapping tolerances, your cluster tolerances, It fixes everything automatically that it can. Again, we talked about cluster tolerances, how you really got to be cautious of what you set up at. Cracking and clustering. This whole process, the way it basically works, is it separates all the individual line segments at the nodes, and then puts them all back together with the nodes, such that there's no dangles or overshots or improper boundaries. Ranks control which features will be moved when things are clustered and which ones get to stay. Classes and ranks are not going to be on the exam, I don't think. Adding topology rules, pretty straightforward. You just select the type of rule and add it in. Once you finish, you validate it. Once you validate it, it gives you everything in red that potentially has problems, and you go back and fix them. Use the topology toolbar to do that. You can use it to fix your errors. You can inspect them, zoom in to see whether it's something real or just some artifact. Controlling selection. If you keep selecting different errors from the ones you're trying to fix with the Fix Topology tool, this property tab will be more selective, so you can control how it responds to what you're doing. You can also add your exception. Dirty areas are areas that have been edited. So if it's set up and it's perfect and it didn't need editing, then it's considered to be clean. This is the editing process. You should be able to basically recite that back. Create topology, validate topology, edit topology, errors. Validate topology again, find any new errors, validate again, repeat till no new errors are found. Rinse, wash, repeat. Rinse, wash, repeat. Alright, so we're covered through the material, and you can see there's a lot of stuff there. It's kind of general, but there are some specific jewels, and there's 12 of them here that we're going to use that could be some sort of final exam question type things. As far as like essay stuff, we're going to use about half of the ones I'm going to go over as the part of your exam. So we're going to go over these. If you have questions or problems, send me an email. Come see me before the next exam. Alright, I'm going to give you something like this maybe, and we'll maybe cover up some of the words, and you got to fill them in. You need to understand length and area, and how when you go messing around with things, clipping and doing overlays and how that stuff can change, you need to know what is and is not updated in terms of area and length. You need to know what the append function is and how it differs from merge. You'll be able to explain what both of these do and give examples of how you would use them and what that means. Model builder. You should be able to recite pretty much this basic 4-step process. Create models, store processing steps for later, execute models repeatedly with different inputs, share models with others, or at least be able to, if I were to ask something like, give me 4 reasons why you would want to use model builder. These 4 would be the ideal example. Might ask you why you want to use rasters. Here is a nice list you can go over that would help. Resampling techniques. We've covered this several times. You need to know all these and be able to explain all these. Remember, distance weighted algorithms. Remember, nearest neighbor is fastest, cubic convolution slowest. Nearest neighbor gives you the most crisp image. Cubic convolution blurs the data the most. Bilinear is always somewhere in between the two. Bilinear uses 4 cell centers. Distance weighted algorithm, cubic convolution uses 16. Nearest neighbor simply finds the closest cell to the existing area where it's going and uses that number. Weighted overlays, know what they are, know how they work. Be able to explain the process of first ranking your inputs, assigning a weight to the ranks, multiplying the weight by the rank, and then adding up to each of the variables after that to end up with your total index. You should be able to explain what interpolation is, and then list the 4 types that are available in ArcGIS. Know how window movements work and know the difference between a block function and a focal function. Be able to explain the difference between a spaghetti model and a topological model. Cluster tolerances. Know what they are. Explain how you could use them to improve editing or creating a data. Understand the editing process. Create, validate, edit, validate, fix, validate, repeat over and over and over.